we go.
Alright, let's get into it. Last time we did we spoke about the difference quotient, we computed some examples. We're talking about functions. We are still going to be talking about functions. I want to talk about piecewise functions. I also want to talk about the domain of a function. Then I want to talk about quadratics and graphing functions. Yeah, okay. That's kind of where we're going. So let's actually do this. So we're continuing our discussion on functions. There's the idea of what we call a piecewise function. So this is just a little bit of a twist on the definition of a function. Because sometimes the rule that we want to apply might change in certain situations. So when we define a function to model a certain situation, sometimes its definition might change at different steps in a process. And so a piecewise function is simply a function whose rule changes based on the region of the domain being considered. So, example, with notation here. So we saw something like this on a quiz before, but the notation is the following. You'll say f of x equals, and you write this kind of notation here. You open a bracket, and you pretty much list different definitions that would work on different regions of the function. So for example, I can have a function that does something like 1 plus x if our x is less than 7. I could have it be 3 if our x is bigger than 7 but less than 9. And I could have it be 1 minus x squared if our x is greater than 9. So, i.e., notice that this function has different definitions depending on where we are. And so basically this is telling us that the important thing is there are 3 different definitions to consider. So there are 3 definitions, right? Or rules, I should say. There are 3 rules to consider, and one would work if your x is less than 7, then 1 plus x is the rule. Just take whatever value you give me and I'll add 1 to it. The second part is if x is between 7 and 9, then 3 is the rule. So that's a constant function. And if your x is larger than 9, it says 1 minus x squared is the rule. So there are 3 different situations here. And you don't really think of them as overlapping, because once you start to overlap things, you have now violated the definition of a function. We know that a function must have 1 input for every output, right? So you can't really overlap these guys. They're totally different definitions and they work in different situations. Now, if someone were to ask you to evaluate stuff, so other than that, there's not really much more to the theory of a piecewise function. It works like a function. It's just that the rule you apply will change based on where you are, right? That's the only thing. So for this particular function, I could, for example, ask you to evaluate, and remember what the word evaluate means. F of, and this is very similar to the quiz problem. Let's say I ask you to evaluate f of minus 3, f of 7, f of 10, f of 8. Okay, so if someone were to ask you f of minus 3, what would you say?
Plus negative.
Come again?
1 plus negative.
You would do 1 plus negative 3. Explain why.
Because it's less than 7. Negative 3 is less than 7.
Okay. So immediately here, when you realize that there's a piecewise function, realize this is going to tell you what your x is. So this tells you that you want your input to be negative 3. And now once you define where your input is, you go to the definition of the function and you realize where does that input fall, in which region. Now, of course, negative 3 is not between 7 and 9. It's not bigger than 9. It's actually less than 7, right? So this applies to the first definition. So this means here, your x is actually less than 7. And so the 1 plus x definition applies here. And so I would simply take 1 plus x, and that would be, in this case, minus 2. Right? In other words, you ignore all the other definitions. At any given time, only one definition is going to take effect, because it's a function. That is the rule for a function. You can only have one output. Okay. Any questions on this? What about f of 7?
Undefined.
Okay. So in B, this asks about f of 7. This, of course, means your x is equal to 7. And so now you start to think, in which group would that fall? Is 7 less than 7? No. Is 7 greater than 7 but less than or equal to 9? No. Is 7 bigger than 9? The answer is no. You realize here that none of the definitions apply. Right? Because this particular x value does not fall in any of those regions. So in that case, what we would say is that the function is not defined for that particular value. And so the answer would be f of 7 is undefined. Now, I saw a lot of people on the quiz, they knew something was up at one of those things that I asked about, but they didn't really know how to say it. So I saw people putting like n/a, it's not applicable, or it does not exist. The phrase used for this situation is undefined. Say the function is undefined. That means you're at some input value where your function just doesn't work, right? Undefined is the terminology for that. So this means you have an input which your function is not defined for. It doesn't understand what to do with that input. There is no rule that covers that particular input. So that would be your f of 7. Similarly, f of 10 would be what? Would be what?
1 minus x squared. 1 minus 10 squared.
Right, 1 minus 10 squared. Here, you realize that your x is 10. Then you realize, well, that means x is larger than 9. This means that the 1 minus x squared definition applies. And so that means f of 10 is going to be 1 minus 10 squared minus 99. Similarly, if I asked you the f of 8, so you read that, you immediately realize, oh, this means x equals 8. This means what region does it fall in? Well, it's strict 8 happens to be strictly between 7 and 9. So you know f of x equals 3 is the definition that applies. And so this means that f of 8 is 3. Just 3, right? That's a constant function. Notice that there's no x to plug in, and so it just stays the same. Now, we'll talk about graphing piecewise functions after I talk about graphing functions in general, so we'll come back to that. But as far as what a piecewise function is, that's basically it. It's just a function where the definition changes based on what region of the domain you're in, right? So sometimes a definition might only be applicable in a very specific situation, but you have one function that's describing this entire situation as a whole. Right? So that's basically it. And just remembering that a function can only have one output tells you that you should only be looking at one definition at a time. Figure out where your input lives, and you ignore all the other definitions and only take that one. Okay, so that is a piecewise function. Another thing that's important to know about functions is the domain, which we defined briefly for a moment. So we said a function is a rule that connects people in one set, which we call the domain, to people in another set. And so I'd like to expand on that definition. So when it comes to actually calculating a definition, you probably want to think of it a different way. So let's talk about the domains of functions. So the definition I told you sort of applies to if you're thinking of the set theoretical interpretation, but I want you to be able to think of the algebraic interpretation, which is, you know, when it comes down to finding the algebra of the situation, actually computing things, how do you want to think of the domain? And you'd sort of think of it in the following way. The domain of f is the set of all inputs x for which function is defined / works. That's kind of how you want to think about it. Okay. So what is the domain? It's the set of all inputs for which the function is defined, or it's the set of all inputs for which the function works. Okay. Now, how do you know something does not work? We're going to actually discuss that. What I specifically mean by does it work or not. But there are two things that you want to worry about here. A very important idea is the fact that domains may be given or implied. Okay. So let's do an example of a given domain. So someone might tell you, okay, here's a function that I want to define. We're going to say f of x is equal to 2x plus 1, and then they add the clause that, okay, for x is between 0 and 1. Right? So someone might define a function for you this way. They told you a formula, but then they further told you where this formula applies. And that basically tells you, that's telling you the domain. Right? Because they're basically telling you, here are the x values for which this rule works. Here are the x values for which this rule takes effect. So they can just tell you, okay, here's the definition of the function, here's where it works. Once they tell you that, it's them telling you the domain. So if I were to give you this and say, what is the domain of this function? You're pretty much going to copy that in, right? That's the easy part. However, there's a notion of an implied domain, meaning they just tell you about a function and they don't really restrict you, at least not explicitly, but you're kind of supposed to figure out where would this function work in general. So the implied domain is that guy. And oftentimes you'd be asked to find the implied domain because it's kind of silly for me to give you the domain and then it asks you, find the domain. Right? Normally, something like that would only probably happen in a quiz on one part of a problem, but to actually have you compute something, that would kind of be silly. So let's talk about the implied domain situation. The implied domain. So you're in this situation. Usually if someone asks you to find the domain of a function, you'd be in this situation. This is if domain is not given, you would assume, right? So you're assuming you don't know, that's why it's implied. They didn't explicitly state it to you, but you're going to assume that this is kind of what they meant. You'd actually infer, or I should say infer, to largest possible set of inputs. Where the formula is defined or makes sense. This is the implied domain. Right? So it's the domain that you assume is going to work based on you considering the question, what are the largest, what is all possible things that could work, right? So I'm not given a restriction specifically, so I'm meant to find my own restriction, and so I'm just going to build, in general, what are the largest possible things? Number of things that I can actually plug in here, and that is said you're finding the implied domain. So usually when they ask you find the domain, it's implied that they want you to find the implied domain. So they're not going to say find the implied domain. They're just going to say find the domain. And if you're not given any more information than that, you would assume that you're doing the implied domain. And so for us, because we don't deal with complex numbers until you get to Math 391. I don't know why, we just don't. So in pre-calc, algebra, pre-calc, calc 1, calc 2, calc 3, you're always assuming that you're dealing with real valued functions or functions of a real variable, which means your implied domain, you're always going to want to think about it as the largest set of real numbers that can be plugged in. For us, this is the largest subset of the real numbers. Right, think of all possible real numbers. So we're going to only consider real numbers that are the guides. That's the largest set. So sometimes they ask you for the domain of a function. One possible answer is it works for all real numbers. Or you can start to take subsets of the real numbers. Let's actually and one important thing to remember here, it's not really going to show up, but just for the sake of completeness, I'm just going to say it. May depend on context. So let me give you an example of what that would mean. So if it says something like, that f of x equals let's actually put it another way. The population. Sorry, I didn't want the number of people. I wanted the population. You're never really going to see a situation like this, but like I probably wouldn't ask it, but I just want to throw it out there that this is a consideration. Measured annually. So let's say this is something, right? So you guys are people who are you're in charge of some sort of census kind of mission in a certain area, and so you want a function to measure the population in a certain area, and you actually take the measurements, you take the census once per year after a certain point after 1980, right? So it's kind of here, the context would imply how would you think of your x and also your y, by the way? What kind of numbers would you think would be possible? All real numbers? What would you say?
0 to infinity for x.
Okay, so is radical 2 a possibility?
No.
So here you would say something like positive integers. Right? It's measured annually, therefore the year, the x value is going to be a number of, a whole number, which measures the amount of years after 1980. Your y you would also assume to be positive integers, because your output would be the number of people, right? You can't have pi people in an area. Right? You can't have 3.14 people live here. I mean, right? You should expect it to be a whole number. So that's kind of something based on the context. If you're reading and you realize, oh, we're counting the number of people or we're doing this, then there are some numbers that are just obviously off the grid. You also can't talk about a negative amount of people living in an area or a negative amount of years after 1980. Those things don't make any sense. So there are some times when you kind of have to be very careful and just don't assume that whatever function you're given will work anywhere. Okay? So it can depend on context. But let's assume that we don't really depend on context, we're really just going based on the formula. So now suppose context doesn't matter. We want to find the implied domain based on the formula given for some function f of x. Now we actually mentioned some of these already quickly. I'm going to remind you what those are. Then we should recall the following. So when we were looking at what an interval is and how to deal with inequalities, we actually found some domains, but I just want to remind you of the rules when you're thinking about this. So for polynomials, right? So this is a very specific kind of function, right? So remember, that's just a sum of terms where your x has non-negative powers, integer powers, and your coefficients can kind of be anything. So, for example, something like y equals 2x to the 7th minus 3x squared plus 12, right? Something like that, right? So we kind of intuitively know what a polynomial is. I believe I defined it specifically for you before. But for polynomials, the implied domain is going to be, what is the implied domain of a polynomial?
All real numbers?
All real numbers. And in interval notation, if I ask you to say that in interval notation, right, negative infinity to infinity, right? So if someone asks you, okay, here's a polynomial, what is the domain? You're going to assume it's the implied domain. What are the largest subset of the real numbers that can work? It turns out any real number will work in a polynomial. Because I can take any number, raise it to the 7th, multiply by 2, and then square it and multiply by minus 3, and then take 12 and add all these together. There's nothing stopping me from doing that. Arithmetic is going to work out with any real number, right? So that's one situation, the polynomials. And then we can talk about rational functions. So we can also deal with expressions here at the moment. So these are functions that look like there's a division involved. Right, so it should be something like p of x divided by q of x. And we call it a rational function if the p and q are polynomials. We call it rational function. Otherwise, we call it a rational expression. Or algebraic expression. And where do these guys work?
Professor,
Yes.
you're asking what's the domain?
Domain, yeah.
It will be parentheses 0, comma, infinity, comma?
No.
Not comma, sorry. Parentheses 0, comma, infinity, close parentheses.
No.
Q of x can't equal 0.
Q of x can be 0. This is all real numbers so that Q of x is not equal to 0. Now you don't even know if 0 is included in that actually. So example, if I look at y equals 1 plus x over 1 plus x squared, domain of that is actually all real numbers. Nothing is excluded from such an expression. Whereas if I ask you y equals 1 plus x over 1 minus x, that's a different situation. The domain would be what? So pretty much you set 1 minus x equals to 0, solve for it, you get x equals 1, and you just know avoid this. Because we cannot be 0. And so you pretty much know that on the number line, 1 is not okay, but literally everyone else is. And so you basically had be able to say the domain is any negative number going all the way up to 1, not including 1. Or we can take any number strictly larger than 1, all the way up to infinity. So that would be the answer here. So if you have a irrational expression, pretty much figure out where the denominator is 0 and avoid all of those points. Right? So polynomials will work anywhere. Rational expressions though, you need to make sure you're not dividing by 0. And this is something I'll explain a little bit later. And we may have to consider maybe I'll just deal with this right now. That answer would be assuming that Q itself has no restriction. I'll do an example of that where Q itself has a restriction afterwards. We'll deal with later. The other kind of function are radicals. And so based on the fact that we know that this is something we've mentioned before, the nth root of x, there are two possible domains to that function. And if we want to find the domain of this guy, the domain of something that looks like that, then we know it is actually all real numbers if n is odd. And it's only the numbers that are strictly greater than 0 if n is even. So this means that if we're looking at a function that looks like the nth root of some other function g of x, then it means the domain of f is going to be the same as the domain of g if n is odd. right? So it'll work whenever the actual function itself works, if n is odd. It would actually be the intersection. And this is how you deal with if your function itself has a restriction. The intersection of domain G and the set of all x where the domain is greater than or equal to 0 if n is equal. Give you a couple quick examples here. So let's say we had something like the following. What is the domain here? All real numbers, right? Because if you're an odd power, you don't really care in general. It's just once what's underneath the radical works, it's going to work. What's underneath the radical is a polynomial. We know they work everywhere. So the Q is just going to say, oh, it works everywhere. If instead I said something like the fourth root of x squared minus 4, now that's a different situation. Right? So at this point, you're going to say, oh, now that's even. Right? So this means you need to figure out where this guy is positive. Right? Technically, it's the intersection between where this works and where this guy is positive, but that is everything, so you just care about that situation. And so that would tell you that your x has to be anything less than minus 2 and anything greater than 2. What's a quick way that I could see that? We actually spoke about that before. Huh? Difference of squares? Why? Yeah, but so you can factor this by difference of squares. If you wanted to solve the equation, you would get x equals plus or minus 2. But how do I know that it's that specific form? Sure. What does that tell you? I mean, we actually spoke about this before, but what will the graph of this look like? So the graph of this would look like that. I know that if I set it equal to 0, yes, I can use the difference of squares and I can solve for that equals minus 2 to 2. But I just realized that if I want it to be greater than or equal to 0, I want these parts here. Right? So in between 2 and minus 2 I don't want, but outside of them I do want. Okay? If this was the opposite way, 4 minus x squared, then I know it would look like this, and I'd actually want between minus 2 and 2. But yeah, technically what you could do here is you could factor this then you get x equals plus or minus 2, then you draw a number line, and then you test values in between. Right? So if it's not something that you can see very easy, there's a nice picture that goes with it right away. You'd probably just go through the motions. We actually spoke about solving inequalities. You'll simply just solve this inequality. And whatever the answer is, that's your answer here. Sometimes the inequality should be pretty easy for you to just visualize the answer. You don't waste time calculating this thing. Let's look at another situation. What if instead I did not just 5 over x. Let's put the same thing. So it's 5 divided by that. So this is what I was referring to earlier about rational expressions. And I said, okay, you literally just worry about where the thing is not 0 in the event that the denominator has no restrictions of its own. Here you'd realize that the denominator does have restrictions of its own. So whenever you see this, you consider all the things that are going on all at once. So one, you would realize that since it's a rational expression, you know that the denominator cannot be 0, right? So this would mean that your x squared minus 4 cannot be 0, which means that your x cannot be plus or minus 2, right? So the denominator cannot be 0, but that's not the only restriction here. We also have another restriction taking place too, since we have a radical. I know that my x squared minus 4 must be greater than or equal to 0. So this means that my x must be a member of the set we found before.
Can you repeat the last part?
Yeah.
You said that must mean that your x is like the last part you said?
Oh, the x must be a member of the set that we found before. Like I'm solving the same inequality.
Okay.
Right? So realize here, there are two things I need to get to work. In one event, I have a division, so I need to make sure I don't divide by 0. In the other case, I do have a radical to worry about, so I need to make sure that works. And so now what you do is you take the overlap. By the way, this is what I referred to earlier as the intersection. Okay. So you're pretty much going to go on a number line. You're going to sketch all your possibilities. So to satisfy 1, we need to avoid plus or minus 2, right? So I would go here. I'd put in minus 2, plus 2. These cannot work, but pretty much anything else can work. Right? And that is to satisfy the first one. Then I look at the second one, and that would say, okay, anything less than or equal to minus 2 or greater than or equal to 2, that satisfies the second condition. And what we want now is the intersection, or pretty much the overlap. We want the space where both the blue and the red line actually worked at the same time. And you'll notice here that what that ultimately means, right? This is the part we care about, where there's the overlap or the intersection. And so at that point, you will have the answer here, finally. It's just going to be, where do they overlap? Well, from negative infinity to negative 2, not including negative 2. So the blue includes negative 2, but this one doesn't, so negative 2 is not in the intersection. Or strictly bigger than 2 to infinity. So the blue includes negative 2, but the pink doesn't. So there's no overlap there, but they overlap with anything bigger. And so that would be your answer here. So all the rules I told you, you can apply several of them at the same time. So at this point, polynomials, radicals, rational functions. So far, that's the only thing we've covered. We're going to talk about exponential functions and logarithmic functions in this class later, and I'll tell you about the domains of those when we actually get there. But at this point, I think that's all the domains you need to know about. Another situation in which we need to worry about the domain is in the case of composite functions. Those kind of have their own little rule. Okay, so remember what a composite function is when you take one function, plug into another function. That has its own little weird domain rule that you have to worry about. So if you consider the function f of g of x, okay? The domain of this function it's again an overlap. Is the intersection. All right, so there's an overlap that you have to worry about of two things. One, the domain of the So the domain of the actual formula for this function, which should be obvious, but people often forget the second part, right? That's not the only rule here. It turns out you have to intersect that with the domain of G itself. So let me give you a simple example where this would apply, where you're probably not going to see it that way. Do I have some? Let me give you a simple example where this would be an issue. Something like, let's say your f of x is the square root of x, and your g of x is x squared. Find f of g of x, b, g of f of x, and their domains. Okay, so let's actually look at this. It's a very simple example, but you're going to see the issues that can arise here. Okay, so first of all, A, what does f of g of x look like? Right, so this is f of g of x, and remember what that means. This is f of g of x, and that basically means you go to the function f, and wherever we see x, we're going to replace it with g of x. So this is just the square root of g of x, okay? Which means it is the square root of x squared. Now if you were to simplify that, what would you get? Well, x. Okay? And so now, if I were to ask you, what is the domain of this guy? All real numbers. B. So here we have g of f of x. Remember, this just means g of f of x. And so this means we go to the function g. Wherever we see an x, we open a void. And inside that void, we're going to put f. So this basically means we're going to have the square root of x squared. If you were to simplify that, what would you get? You get x. Now, if I ask you what is the domain of that?
Is it all real numbers in it?
Now that would be what you would assume, but that is incorrect. Why is it not all real numbers?
Because you cannot have a negative square.
Right, because in the green section, so this is where the lesson is coming from, right? So I plugged in that into this function, which means this is the number that I'm plugging in that I simplified to get here. Notice, therefore, that there's a radical that's in play. The thing is, I kind of simplified it so you don't see it, but originally that's what it was. Now, originally, if I'm plugging in an x into this function, it would have to work in the green part, right? It would have to work in all possible definitions of the function. However, here, what happens? Not all x's actually work here, right? So, the fact that, what x's does work here? It has to be 0 or bigger, right? So the fact that I simplified and now it looks like a polynomial, it's not really a polynomial. It's half of a polynomial. It's only the half that deals with the 0 or bigger, right? So here you had to worry about the domain of the input. So the domain of this is actually going to be 0 to infinity. Now, both of these after simplifying looks the same. But what you need to remember, and this is very important, this shows you that simplifying does not fix a domain. Right? Negative numbers couldn't work here, they're not going to work there either. So just because you have something and you simplify it to make it look like something else, you have to worry about the original construction, right? So in the first place, I couldn't plug in a negative number. So even after I simplify, I still can't plug in a negative number, right? Pretty much, I'm taking the outputs of this function and plugging it into f. But the outputs of this function would only work if the input itself was 0 or bigger. So therefore, this original x that I'm plugging in here, this original x has to be greater than or equal to 0. So my x here is not really an x. It's an x where it has to have been greater than or equal to 0. Okay? So that's something that they can kind of try to trick you and catch you on. So sometimes they ask you to find a composite function and you might simplify it, but then in simplifying it, you erase an issue that was once visible, but now after simplifying it's no longer visible. It turns out that the issue is still there. Just because you write it in a nice form doesn't mean that you fixed all the issues with the function, right? Negative numbers didn't work in the beginning, they're not going to work in the end, right? So that's a very important thing. So while these two look the same, they're not the same. This x can be any possible value because anything can work in x squared, and then it's going to give me something that's greater than or equal to 0, and then the square is going to work. So here, both the inside and the outside will work, right? Here, the inside didn't work. So you have to worry about, oh, what values where the inside's not going to work. And that's what I meant. You need to take the intersection. not only of the formula of the composition, which might be simplified, but of the inner function itself. Because if the inner function is not going to work, then it's not going to give you a meaningful output to be able to plug into the other one, right? So you're not going to be able to have that connection, right? Remember how we looked at what g of f meant, right? This was the function where g did something here, and then f did finish the job. But over here, the negatives didn't work. Right? Over here, like, I'm just going to say the negative numbers are in the red part. The negatives didn't work. So now, if you look at the function as the composite function, the guy that has domain over here and goes all the way over there, that is f of g. But look, the negatives didn't work in the first place. So they're not going to work with the blue function. Right? So that's an important lesson there. Simplifying doesn't fix your domain issue. And how you actually work around that is that you have to realize that for a composite function, you have to worry about the domain of the inside first. Then look at the domain of the outside, and you have to overlap them. Any questions on this idea? Okay, so it's just like when you plug one function into another, worry about the domain of the thing that you're plugging in, because that will always apply. So even if you simplify and make it look pretty, and you're like, oh, this is just a polynomial. It doesn't. No, it's not a polynomial. It's half of a polynomial, because there was a part of the domain that didn't work in the first place. It's not going to work if you cut out the middle, right? It's still an issue. I believe that's all the situations you have to worry about the domain for the next test. We're going to talk about, like I said, we'll talk about new functions with new domain rules pretty soon. Exponentials and logarithms, they have their own domain requirements, but we'll deal with that as they come up. This should cover everything that's on the test on Wednesday in terms of domains. Okay, so I want to go a little bit out of order at this point. We're going to jump into a section of chapter 3 and then come back. It's going to be okay. It's something we have also discussed before. Basically, it's quadratics. So 3.1, quadratic functions. So recall, a quadratic equation is one of the form. So if someone says, what's a quadratic equation? It's an equation that looks like this. ax squared plus bx plus c equals 0, where your a is not equal to 0, and your a, b, c are constants. A quadratic function arises when you don't only care about where this hits 0, you want all possible outputs of this kind of expression. So it's simply when you say f of x is equal to ax squared plus bx plus c, right? Which you may call y. So when you're not forced to make this side 0, you just make this some other variable where if you're plugging in different values of x, you can compute a bunch of other values. We call that a quadratic function. And again, a naught equals 0, a, b, c are constants. So a quadratic equation means you have an equation of this form. That means you're looking for a specific output, essentially. You can group everything so that it would look like this. If, however, the other side is another variable, we call that a quadratic function. It will be a rule. I can get an output y by computing this expression. Now we spoke a lot about this equation. We spoke about how to solve it, how to complete the square, how to, what is the quadratic formula, all of that. So remember all of that. Just say recall what we learned about quadratic equations. Okay, so this means you should know how to solve one, how to solve. This means you can factor, you can complete the square, you can use the quadratic formula. I also want you to remember by completing the square, you sort of realize that there was, in either case, there's a smallest or largest possible value. So if our x equals minus b over 2a, this gives the largest, and it gives the largest if a is less than 0 possible value. Of y, or the smallest possible value of y in the event that your a is larger than 0. And I also want you to recall the point. If I look at, if the input is minus b over 2a, and I compute the corresponding output of that, f of minus b over 2a, that point is called the vertex of the quadratic. So now, I'm not going to go over that. We went over it, we did a bunch of examples, we put it on quizzes so far, everything. Okay. What I want to talk about now is the graph of a quadratic. Hey. Pay attention, stop talking. Let's talk about the graph of a quadratic function. For one, it's so special that we actually give it a name. Graph of a quadratic is called a parabola. So when you start to graph a quadratic, you draw that picture in the xy plane. The shape of the picture, it's called a parabola. It's worth mentioning here technically it's not correct, but parabola and quadratic are often used interchangeably. Right? So it's something that's accepted, it's traditional. Okay. But usually when someone says parabola, they're specifically thinking of the picture, whereas when someone says quadratic, they're specifically thinking of the equation. But because the picture is such a useful thing, normally when people think of an equation, they automatically imagine the picture. It's very common for us to just use it interchangeably. But the word parabola really refers to the graph, the shape of the graph. It's kind of like you would have this equation, and someone will call that a circle. Technically it's not a circle, but it's just, once they see that, they imagine this, so they're like, oh, it's a circle. The circle is the name of the picture, right? So that's that. Now, as I said, you don't want to be one of those people when you're graphing this, they're plotting like 10 points. There is a very efficient way to graph parabolas. So we're going to talk about that. And it requires that at most, worst case scenario, you're going to plot 3 points. Worst case scenario. If you're plotting more than that, you're wasting time. And it means you kind of don't know what you're doing. So, very important. All right, let me say how to graph a parabola. So how to graph a parabola. First step is to note the sign of A. It gives you the shape in the following way. If your A is positive, if I have to tell you to be quiet once more, I'm going to ask you guys to leave. If A is positive, the shape of the graph is going to look like this. If your A is negative, the shape of the graph is going to look like that. So once you look at a quadratic equation, you should automatically see a certain shape in your head. If the number in front of the x squared is a positive number, that's going to be what the picture is going to look like. If the number in front of the x squared is a negative number, that's what it's going to look like. It's always going to be one of these two shapes, right? So it means that you don't need to plot a bunch of points to figure out what the shape is. You just know the shape is going to be this or the shape is going to be that. Now I need to find just a few key points to draw that shape through, right? So that's how you want to think of it, right? So I'm going to draw a parabola or a quadratic equation. I know it's either this shape or that shape. I just need a few points to know where I should draw those shapes through. So that's the first step. Now step 2 is to find the intercepts. Now we've spoken about that already as well. We realize that the x-intercept, this is the set y equal to 0, solve for x values. And to find the y-intercept, you set x equals 0, solve for the y values. So you need to find those 2 points. Well, it can be a maximum of 3, right? So let's do a situation. Let's talk about some examples here. So let's say your graph looks like this. Then it means by finding the intercepts, you would have located this point, and that point, right? So you get 3 points. you could have a situation where your graph does something like this. Can just touch that and then go back up. So with the intercepts, you would have discovered this point and that point. Right? So in that case, you would only have 2 points to draw the thing through. You could also have a situation like this, where to graph the intercept, get the intercept, you'd have only discovered this, right? So here are 3 possible situations, right? You can actually only find, you can find 2 distinct x-intercepts and 1 y-intercept, or you can find 1 y-intercept, 1 x-intercept, or you can find the y-intercept but no x-intercept, right? So for any quadratic you will get, they will fall into one of these 3 categories. You're either going to only be able to find 1 point, 2 points, or 3 points. You will never need any more than that. Okay. So now, so this is illustrating case 1, case 2, and case 3. Now case 3 is sort of weird. How would you know how to graph it if you can only have 1 point? Is that really enough to actually graph one? So this is kind of step 2b. If there are no x-intercepts, like in case 3 above, in this case you would find the vertex as the second point. And so what you would have then is you would have the situation where you have the graph looking like that, and you found this point by finding the intercepts, but because you only have 1 point, what you would do is you would find another point, which is the vertex, which you are now going to think of as the lowest or the highest possible point, and that you will know based on the sign of A, right? So the yellow point, this will be max point if your A is less than 0. It's the min point if your A is greater than 0. Which finally brings us to step 3. Sketch the appropriate shape from step 1 through the points found in step 2. And that's it. So graphing a parabola is a 3-step process. You will first know, should it be inverted or regular. Usually we call the regular one this one, where it opens upwards. We call it an inverted parabola if it opens downwards. So you should first figure out, is this inverted or not? You only need to look at the A value to figure that out. If the A is negative, it's inverted. If the A is positive, it's regular. 2, you need to find the intercepts. You can have a maximum of 3 things that you're finding at this point, but you could have 2 or 1 thing that you're finding at this point. In the third case, oftentimes we actually identify 2 points on a parabola. If you have to identify 2 points, the second nice point would be the highest or lowest point. Because a lot of times we actually want to use that in some other context. Let's do some examples. So dealing with a quadratic function is kind of like dealing with, algebraically speaking, it's kind of like dealing with a quadratic equation. When it comes to graphing it, it's a 3-step process, as I just outlined. So let's actually do some examples here. sketch a y equals minus 2x squared plus 12x minus 10. Y equals x squared minus 2x plus 2. Okay, A. So the goal here is to sketch this function. So the first step I'm going to write in a different color because it's what you would think, it's not necessarily something you would write down. Although you can do something to remind yourself, just do it to the side to remind yourself. So in step 1, I will notice that your A is minus 2. This implies what's the shape? Inverted. It opens downwards. So that's always in my mind. I will never forget that. It's important that you make note of this because sometimes when you're solving the equation, you might change the situation a little bit. So just step 1 is to notice what it is. Okay, so now step 2, you're going to find the intercepts. So start with the y-intercept is easier, so you can do that first if you want. So what's the y-intercept here? Y equals minus 10. Right? Just plug in x equals 0, got constant terms. It's always going to be the c in the general formula. What about the x-intercept? How would you find the x-intercept? Well, for x-intercept, you plug in y equals 0, and then you need to solve for x. So for the x-intercept, you need to solve minus 2x squared plus 12x minus 10 equals 0. Okay, so now let's talk about that. So first step here, you might just divide by minus 2, right? Because 2 goes into everything. I would get x squared minus 6x plus 5 equals 0. And here's why part 1 is very important. Every now and then, what I see on an exam is that I gave them a picture like this, but in solving for the x-intercept, they made the x squared positive, and then they drew this, right? Because they forgot to say, oh, make sure it's negative, make sure it's... And then they lose track of that, and just because they're solving this equation where it's positive, they think, oh, it's this way. That's why I put in step 1. Make sure you know what it should be, because you might get rid of that sign in part 2, but it doesn't matter if you got rid of the sign. The original had the negative sign. Okay. Now we can solve this, which at this point should probably be no problem. We should be able to factor this. I think 5 and 1 would work, negative on each. Right? And so here you get x equals 5 or x equals 1. So now we found 3 points where it touches the x and where it touches the y. And so now we can actually sketch that. Should have left more space. But basically the idea is, at this point, I realize that this is just going to go, I know this is the shape I want to draw, and I want to draw it going through those 3 points. So pretty much I'm going to sketch that. Because I know the shape, I just have to figure out the points. It's going to go through minus 10, it's going to go through 1, it's going to go through. Yes,
How can you tell how high the vertex will
doesn't matter. It's kind of like a situation, if the only problem is the sketch, I mean, there might be a question that might ask you about the max point, so you actually find that coordinate, but in general, if the question is the sketch, you don't care. Okay? And you don't even really care about technically how high it should be, because that's kind of like in the situation where, you know, students will want to figure, oh, exactly how high it should be, but you're never going to be able to sketch anything accurate. You're not a computer, right? So the height to scale doesn't really matter, right? If I ask you to sketch it, you find those 3 points, you draw the shape through those 3 points. In B, I would have y equals x squared minus 2x plus 2. First thing I would notice here is my a is greater than a equals 1, which is greater than 0. So that means the shape is going to be like that. So I know that already. 2, I'm going to find the intercepts. Y-intercept is 2. X-intercept, I'm going to actually solve x squared minus 2x plus 2. And you might try to factor that, x and x. To get a 2, you need a 2 and a 1. But you can't use 2 and 1 to get 2. No, not factorable. Okay, so maybe we have to use a quadratic formula. So the numbers might have radicals in them, that's a possibility. So let's use the quadratic formula to figure that out. So here we know that x is equal to minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. You notice this is no real solution. Right? What's under the radical is negative. So pretty much this is the only point I have to go by, just there's a 1 point. Now at this point I can actually sketch it, right? Because that's fine. I just know I have a shape like that going through y equals 2 that never actually touches the x-axis. But now what you'd realize that there are actually 2 possibilities, right? I could have a picture doing like this, or I could have a picture doing like this, right? So how do I know which one? Is it on the left side or the right side? Well, what you do is you find the vertex. Now the vertex is going to be x equals minus b over 2a. That is going to be 2 over 2. So the vertex is going to occur when x is 1. So I know at this point, that's the picture. It looks like this. It never actually touches the x-axis. Now if I need to find this particular point, I would just plug in 1 into the original. Y would be 1 squared minus 2 times 1 plus 2. And that would be 3 minus 2, that's also 1. So this point here is actually 1 comma 1. The last one is pretty much like the first one. Let's just get through that quickly and then we'll wrap up.
You have the quizzes, or are you posting them online?
I already posted the answers. I do have quizzes to give back. Okay, so let's really finish this up quickly. Okay, so y is equal to x squared plus 6x plus 5. I'd realize, oh, that definitely looks like this. So then I'd realize what the intercepts are. Y equals 5 is the y-intercept. And then I have x squared plus 6x plus 5 equals 0. That would factor. I would get x plus 5, x plus 1. So my x would be minus 5 and minus 1. And so the picture is going to be like that. where this is 5, this is -1, that's -5. How many seconds did that take? That's how fast you should graph a quadratic. So when I'm giving you in a test, I'm like, okay, this is like a 10-second problem right here. Graph this quadratic. It didn't take any time, right? But if you really know the 3 steps very well, and of course you know factoring very well, which I would assume by now you do, it's not going to be a big deal. Graphing parabolas, which we'll talk about next Monday, is going to be a big deal. So that's also something I'll mention for the test. So technically our test covers, according to the syllabus, it also covers inverse functions and graphing parabolas. So that's not officially going to be on it because we didn't get it. So everything up to here is fair for the test on Wednesday. So what I'll do is those problems that talk about, ask you about the inverse or to graph some weird thing that I never showed you how to graph. So if you need to graph a straight line or a parabola, that's fair, right? But to graph something else, I'll push those to the bonus section.
Professor?
Yeah.
This is 2
This is 3.1.
Okay, the one before that you covered, which
2.2 or 3?
that was the one I feel like
Okay. Let's give back quizzes. What? Oh, okay, stop.
the whole time.